Hey guys, so in this video we're going to talk about barometers, which are classic pressure gauges in physics. Let's check it out. Alright, so pressure gauges are devices, they're instruments that use height differences to calculate pressure. And most of the time we're going to use this equation right here. Alright, so this is what a barometer looks like. I'll quickly describe it. It's got a container here, sometimes called a reservoir, fancy, right? That's where most of the liquid's going to be. And there's sort of a closed pipe here. This is typically referred to as the column, or because it forms a column of liquid here, right? So the idea is that you have the bottom part here exposed. So this part here and then this part here are open, are exposed to air, so that air molecules around here push down against the liquid and cause it to ride up this pipe, ride up this column, okay? And what you do here is you then measure the height difference between the very top of the column and the very bottom of the column, which is over here, right? This part here is just to have extra liquid, so don't worry about that. So once you have this height difference right here, you are then able to use this equation. P bottom equals P top plus rho g h. I want to remind you that this is the density of the liquid, not the density of the air. Cool? So let's see. The pressure at the bottom is the pressure over here. And because this part of the liquid is touching air, this is the pressure of air. Sometimes also referred to as just the atmospheric pressure. And the pressure at the top is this here. And because it's touching vacuum, the pressure is zero. Whenever you're touching vacuum, the pressure at that point is zero. So this is just zero because it's vacuum. So you're left with rho g h, and that is the equation. It becomes simpler. Now, if you are trying to calculate pressure, you would use a known liquid. Let's write this here. You would use a known liquid so that you know its density. You can plug it in. You're on Earth, so you know gravity, or if you're somewhere else, you would presumably know gravity. And then the H you measure, I don't know, with a ruler or something, right? And you measure H, and that allows you to then find, P air. So this is a device that's used to calculate the pressure of air. Now you might be thinking, isn't the pressure of air just 1 atm? Well, not really. If you go up really high on a mountain, you have lower air pressure, so you can carry your little barometer with you, and you're able to figure out the pressure in different places. Cool? So that's how the barometer works. You should know that the classic barometer invented by Torricelli uses mercury instead of any other liquid because mercury is heavier. So why does that matter? Well, you need a column. This column of liquid here has to be tall enough to push against the air pressure until it balances itself out, right? And mercury is very heavy, so you don't need that much mercury. So that column doesn't have to be that tall. If this was water, let's write this here. If this was water, the column would have to be 13.6 times taller. Okay, and usually when you build a barometer, this thing is about 1 meter high, which is about this much, right? With mercury. Now imagine something that's 13 times bigger than this, and I gotta carry this freaking thing around, right? So that wouldn't be very good. So they figured, hey, let's just put the heaviest thing we can think of. They put mercury in there, and that's why it works like that. So let's do an example real quick, very straightforward, and you'll see 2 different ways you can get a question about a barometer question. So it says here, a classic barometer, as shown above, is built with a 1 meter tall glass tube and filled with an unknown liquid. So this is an unknown liquid. I just told you that you're supposed to use a known liquid, but here we're going to use an unknown liquid, but it's going to be okay. So let's just draw a thing here. Very simple. And this thing here is, it's 1 meter. So whenever you talk about height, it's the height of the column over here. I'm actually going to draw this over here. This is 1 meter. And you fill it up with a liquid. It says the liquid goes 76 centimeters up the glass tube when the barometer is exposed to standard atmospheric pressure. So I'm going to draw a little liquid here. We're going to make it blue. And we're going to say that this liquid goes 76 centimeters high. Okay, so this is going to be 76.76 meters which means there's a little bit left here. You don't really need the calculator, but it's 24 meters. Okay, and the height is always from the base of the tube to the top of the liquid. Okay, cool. So we want to know what is the density of the liquid. So what is the density of the liquid? And again, we're always going to use the pressure equation. P bottom equals P top plus rho g h. I just told you earlier that the rho is known so that you can find P air. This problem, we're flipping that. I am telling you what the pressure at the bottom is. I'm telling you what P air is because I told you that it is standard atmospheric pressure. In other words, this is just 1 atm. The pressure at the bottom is 0. And now I'm giving you this and asking for this. So we're just flipping the equation around. That's fine too, okay? So let's move some stuff around here. The density will be the pressure of air divided by, the zero's gone, divided by G times H. Pressure of air is standard atmospheric pressure. Well, remember, you can't plug in 1 atm. You have to plug it in Pascal. And 1 atm is 1.01 times 10 to the 5th Pascal. Gravity is, I'm going to be precise here, 9.8 meters per second squared. And the height is this height difference right here, 0.76 meters. Okay? Now, when you divide this, you're going to get 13,560 kilograms per cubic meter. And if you were to look this up on Wikipedia or Google or whatever, you would figure out that this is actually the density of mercury. Okay? This is actually the density of mercury. So this is mercury. Cool? So just like how you can put a known liquid and figure out what the pressure around you is, you can also have a known pressure and then figure out what the liquid is. So you can do both things. So let's look at part B here. Part B says, when the same barometer with the same liquid is taken to a different location, the liquid goes up 84 centimeters. The liquid goes 84 centimeters up the glass. So you go somewhere else. Okay, you go somewhere else, and now this thing is going 84 centimeters up the glass. I'm just going to draw this real quick. And the idea is that this is now 0.84 centimeters. And the question is, what is the atmospheric pressure at this location? So the first place had standard atmospheric pressure, but now we want to know what is the pressure of air in this other place. Okay, so again, P bottom equals P top plus rho g h. P bottom on a barometer is always going to be the pressure of the air around you. P top is always going to be 0. And then we have rho g h. Here we're looking for the pressure of air. I know density because it's the same barometer with the same liquid. So the density is going to be this right here, 13,560. Gravity is 9.8, and then the height is 0.84. And when you multiply this, you're going to get 112,000 pascals. Okay, so instead of it being, which by the way is 1.12 times 10 to the 5th Pascal, and if you convert this to, if you want to convert this to ATM, you can just do 1 ATM is the same as 1.01 times 10 to the 5th. And this will tell you that this is 1.1 atm. Okay, so the liquid went higher, the liquid went up higher, which means that the pressure of the air outside of you is stronger, which pushes the liquid farther up. And this is verified here because here we had 1 atm, here you have 1.1 atm, so it's about 10% higher. That's why this thing went up about 10% higher as well. That's it for this one. Let's keep going.